Okay, I think we can begin. I think we have some good numbers to start. So my name is Victor Ndusi. I'm a consulting research fellow for HEI. I'm based in Nairobi, Kenya. Thank you all for joining. And as we begin, you can share your name and institution in the chat. A couple of housekeeping announcements as well. We'll be um, anticipating your questions through the Q&A function. Please do send them over as we progress. The slides, and we are recording this session, so this will be available for those who may have registered and not been able to join as a recording posted on our website. I will share the link towards the end of this presentation. So all the material presentations will be made available to everyone after this. So as we begin, I want to take a few minutes to just go briefly through HEI and what we do. Then we can begin today's session and build up to, why we are here today. So HEI is a nonprofit. Our mission is really a healthy environment to all. We do this through three programs at the Institute. We have an energy program, an environment and health program, and a global initiatives program where I belong. So I will focus mostly on the global initiatives work that we do in various regions, Africa being one of them, South Asia being the other. So we do this through various things you might have seen already, or you may be familiar with the State of Global Air report that we do. So this is essentially bringing you high quality data on air pollution exposure and health impacts globally. We have done a report for Africa as well in late 2022. We also do have a lot of work on scientific capacity, which is essentially why we're here today, strengthening capacity for conduct locally relevant research. We also do have now, thanks to a funding call that we issued about a month ago, we're going to hopefully fund some studies in East Africa in the near future as well. Evidence synthesis tailored to inform national and regional policy decisions. Example here that I'm giving is a latest recent published in April 2025 scoping review of air pollution and health work in evidence in East Africa. We are embarking on a similar one for West Africa this year, hopefully publish that next year. Lastly, but not the least, collaborative networks. We sort of, in our way of doing work, we do encourage and support collaborative networks in the regions and the spaces where we work. The example for Africa, of course, is the Africa Clean Air Network. A lot of you on the call may already be familiar with the Africa Clean Air Network and the annual forum, the Africa Clean Air Forum, this year happening in Pretoria. We are also looking forward to seeing some of you, if not all of you, at the forum. So this is just to give you a sense of what we do for Africa under the Global Initiatives Program. And moving on to today's topic or training series. So as part of our sort of capacity strengthening work that we are doing in the region, we really thought about, and we've had a lot of, needs and workshops that we've held across East Africa. But this training series is really open to the region. So we've planned for 4 sessions, 2 weeks apart. This is the first session. And the idea is for us to look through the whole spectrum of air pollution work, all the way from monitoring. How do we do that? What are the techniques involved? How do we approach exposure assessment for health purposes? And then we have an introduction to epidemiology or EP 101 session in June 16th. And then we close that off with a really practical session on how do you actually design air pollution epi studies. We'll have several presenters for that one, giving us real life sort of examples where that has happened on the continent. So we are looking forward to seeing you at not just today's session, but future sessions to come. So today's agenda, all the sessions are designed as 1.5-hour sessions. It's mostly lecture style sessions. So the welcome, which is what I'm doing right now, we'll have a 50-minute sort of lecture style presentation next. And then we really want to open it up to questions and discussions and hear from you all in terms of how your experience has been on the air quality monitoring space, both for gaseous pollutants and particulates. And then hopefully we can close on time as well. So really looking forward to the discussion today. So as I finalize, I'm really the host for this session. I'm not really the speaker, but I would like to invite Dr. Bridget Language, based at the Northwest University. Her expertise spans from air pollution, atmospheric science, climate change, among others. So she'll be talking to us about the various techniques in air pollution monitoring. And will really take us through both the techniques and the methods and the technologies available for both gaseous pollutants and particulates as well, and really set up for, set us up for the sessions to come in terms of how we move then from what you're seeing in the ambient environment to applying that to health impacts and the health outcomes that we sort of attribute to air pollution exposure. So I will hand over to Bridget to take us through our lecture for today. Welcome, Bridget, and I will stop sharing my screen.
Thank you, Victor, for the introduction. I really appreciate it. Let me just get my screen shared as well. I just want to make sure that my sound is very clear.
Sound is good, loud and clear.
Perfect. Thank you very much. So as mentioned by Victor, my name is Brigitte. I'm an associate professor at Northwest University based in Potchefstroom, South Africa. My focus is on anything air quality related, mostly measurements at ground-based level. And today I would like to provide you a little bit about, with an overview of air quality monitoring that will include the different technologies as well as methods and study design choices that needs to be taken into consideration when approaching any type of air quality related study. The focus of this presentation will be mostly on ground-based monitoring of both particulate matter and gases, and I will highlight a few African case studies as well. First of all, I would just like to show you a little bit about what I've been involved in. It's not mainly just in South Africa that I've worked, even though most of my work is based here. I have been involved in international collaborative studies, a lot of those in Southern Africa, as well as in France, where the projects included both ground-based monitoring as well as aircraft-based monitoring and satellite monitoring. So first of all, the presentation is not supposed to give too much detail on the different technologies themselves and how they work. It's more to show the wide range of technologies available and where they fit into the different types of pollutants that we actually want to monitor. And by the end of the session, ideally, I would like you to have the ability to actually look at your potential study and see what methods could be applicable to you. You maybe have not considered something that that I mention in this presentation going forward. And just to kind of understand that there's more than one approach that can be taken. And these approaches typically differ for our African-based studies due to a lot of different limitations that we have compared to more Asian or American-based studies where the resources are more wide and available. You know? So first of all, air pollution itself and the pollutants that we look at mostly consist of particulate matter as well as gaseous particles. And these occur in a wide range of particle sizes across a spectrum. And depending on what our interest is, we could focus on the nanometer up to a core size particle fraction. And depending on what we look at, that will determine what type of monitoring approach we will take and what type of technology we need to consider to actually measure those particles that we are interested in. In this framework, I'm mostly going to focus on the sources, emissions, and concentration, and then look at a little bit about how we go about doing ambient monitoring versus indoor monitoring and personal monitoring, and how that fits into an overall, for instance, household air pollution aspect, where we consider all three of those combined. I will not focus so much on the exposure and dose, as well as health effects part of that, as that forms part of the upcoming webinar series. One key driver in the methods and technologies that are used to determine the pollutant concentrations is mostly related to the actual physical and chemical properties of the pollutants that we are interested in. So those properties drive the technology and how the technology works, and also how we will go about interpreting or deriving the actual concentration values that we're working with within those instrumentations. So what do we normally measure? For us as air quality scientists, that is mostly driven by either our policy or our research questions that we have. Within the policy framework, we usually look at the primary pollutants, which include particulate matter, usually PM2.5 or PM10. And those are usually derived in mass per volume, such as micrograms per cubic meter, and also reported as such. For aspects like black carbon and those variables, those are more intricate and not often recorded in general policy or regulatory requirements. And mostly within these particulate matter measurements, we look at sub-minute, hourly, or 24-hour values due to the fact that we have to compare those to national standards or guidelines. Similarly, for the gases, we mostly look at NOx, ozone, sulfur dioxide, sulfur dioxide, carbon monoxide. We typically report these as mixturing ratios in ppb or ppm. And these can be measured using different approaches, such as passive samplers, which integrate over a few weeks, or as continuous measurement, which are generally given in minutes to hourly values. As we look at this table, I want you to look at the fact that we have no single technology that covers all the pollutants that we monitor. For particulate matter, we usually look at three main reference equivalents. These include gravimetric-based monitoring, beta attenuation, as well as tapered element oscillating microbalancers. For black carbon, these include things like your ethylometers, your multi-angle absorption photometers. For your gaseous pollutants, they range from chemiluminescence to UV photometry or non-dispersive infrared technologies. Within the low-cost developing aspect of monitoring, these are usually divided into optical particle counters for your PM or scattering nephelometers. For your gaseous pollutants, it's mostly either electrochemical sensors or metal oxide semiconductors. For your integrated or passive sampling, we usually look at things like minivol samplers, passive diffuse samplers, or stain tube measurements for occupational fields of study. And then additionally, we can incorporate things like satellite measurements, looking at, for instance, the AOD, the aerosol optical depth when it comes to particulate matter. We also have different total column measurements that we get from different satellite platforms as well for gaseous pollutants. So I'm going to break down some of the main aspects a little bit further for this. The first one we are quite interested in a lot is the reference PM, so reference particulate matter. And for this, the gravimetric-based measurements are considered the gold standard. Usually for this, we look at having size-selective sampling. We can have specific size sampling done for instrument for instance, only focusing on PM2, but we also have instruments that can do size selective sampling across a range of sizes, for instance, PM1, PM2.5, or PM10, depending on the inlet and flow rate of the instrument. Usually gravimetric sampling is done over a set period of time. So this is where you have a filter within the instrument exposed for either 6 hours, 12 hours, or 24 hours, depending on your time period of interest. These filters are usually weighed prior to and after exposure within a laboratory setting, as you can see in this picture to your bottom left. This is a clean lab where we have microbalancers set up to a very, very sensitive scale, and we can measure up to microgram deviations in collected particle mass. These weights are then used to then calculate the actual concentration of particulate matter captured onto that filter over the period of time. The strength of this method is that we have a traceable mass. So there's nothing in between there's no technology in between the actual mass being deposited on the filter and getting the measurement. However, we do need to think about other influencing factors, such as your laboratory environment that can have an impact, your sensitivity of your scales, etc. With gravimetric measurements, I think the biggest limitation that we have is the impact of the actual lab technician doing the work, right? So the person doing this work needs to be very meticulous in what they do and how they do it. Otherwise, errors do tend to creep into gravimetric mass very easily, especially in the weighing, pre-weighing and post-weighing processes. The limitations surrounding gravimetric mass measurements also include things like it is a time integrated measurement, so there is no real-time data. It is labor intensive usually to do, so it takes a lot of time. You have to pre-weigh in the lab, expose in the field, come back to the lab, post-weigh, then only do the data processing, and that can delay a project quite if that is your main form of data collection. One of the other limitations that we have is depending on the time between exposure and weighing, you do sometimes have a loss of your semi-volatile compounds from the filters due to chemical interactions. Okay, so those are some of the things that we need to consider when thinking about gravimetric-based sampling. A nice example of what these filters look like is to your bottom right. We have quartz filters that have been exposed in the Vaal Triangle region, which is a priority region in South Africa. These samples are 12-hour samples, and as you can see, we have a very clear deviation between the exposed and the non-exposed sample in this picture. As we move on from the gravimetric-based sampling for particulate matter, we now look at the continuous near real-time mass calculations based off of either the beta attenuation process or the tapered element oscillating microbalance. These are the two most used continuous methods of measuring particulate matter. These instruments usually have a wide range of bin sizes that they can actually differentiate within their sampling, which also provides us the ability to actually choose which measurements we want to focus on. So we don't have to pre-select a inlet size, for instance. They most of the time have a main inlet and the separation happens within the measurement chamber, depending on the instrument type. Just keep that in mind. So for the beta attenuation, these monitors usually estimate the mass from the attenuation of beta radiation through particles collected onto a filter tape. And these can be provided in usually hourly intervals, and they are widely used in regulatory networks. Specifically in South Africa, almost all of our monitoring regulatory network monitoring stations do have beta attenuation instrumentation. The TIOM in itself uses an oscillating microbalance. What this means is that as particles collect, the oscillating frequency changes within the instrument, and that change is then converted into a mass concentration. These are sometimes affected by your temperature and relative humidity within your environment. So most of these instruments also come with the option of having a aerosols when using these instrumentation. Yeah. So I think the key takeaway for me here is that both the beta attenuation and TIOM technologies are considered either reference or equivalent methods within the different jurisdictions. This could be like the US EPA, the EU, etc. And the important thing here is that even though they are considered reference or equivalent methods, they do still have limitations and uncertainties associated with them. So yes, we consider them reference values, but we cannot report these values without having some sort of error estimation associated with it. And these error estimations are highly impacted by the specific environment in which you are sampling. So your synoptic and local weather and climate conditions play a huge role in how these instruments perform as well. Next, we're going to move on to the instruments used for the reference gases, right? So typically within the continuous measurements, we use analyzers for this purpose. These analyzers, again, run on different technologies. For NOx, it is usually chemiluminescence, ozone in itself, usually a ultraviolet photometry. We have SO2, which is pulse fluorescence, and then carbon monoxide, which is NDIR, so non-dispersive infrared. Right. These instruments in themselves, again, they usually measure continuous measurements every few seconds, and we can then average it over the time period that we require the data, from minutes to hours to days, depending on the application. I'm not going to focus too much on the gas analyzers today. I just wanted to just highlight how these differ from the particulate-based instruments, which is the main focus. One thing to remember with these analyzers and the continuous analyzers is that these instruments tend to be very expensive. They all require some sort of shelter, so that is where we get our air quality monitoring stations from. And they require traceable gas standards for their calibration, which means that every few months, or depending on your manufacturer specification for that specific instrument, you would need to do dynamic calibrations, zero span checks to make sure that you account for the instrument drift over time, and you keep that instrument as a reference or equivalent method. If you don't do these monthly, bi-monthly maintenance with regards to calibrations on them, your instrument is no longer a reference instrument. Okay, so it's very important that you keep those aspects up to date on your instruments. It's not a plug and play. You can't just install it and let it run for 10 years and not do maintenance on it. It doesn't work like that. Then it's basically useless. You can't use the data. Okay, you can't compare, for instance, low-cost sensors to that data because there's no basis for the comparison. You are not sure that your reference instrument is actually reading reference values. Okay. So please be sure that you take that into consideration. The other thing surrounding both the PM and gas continuous measurement is the fact that it has an extremely high operating cost. So because of this maintenance that has to be done on a regular basis, and the consumables that these instruments use, and the fact that most of these instruments are not manufactured anywhere in Africa, most of the time, the parts, the instruments, the consumables have to be imported either from the US or from Europe somewhere, and it adds up. Right? For shorter campaigns, for 6 months, a year, it's more manageable. But if you think about keeping it as a reference station, which is set up and maintained over 10, 20 years, the cost can be consuming. Okay. Next, if we look at more passive or integrated sampling methodologies for gases, we start looking at things like a diffuse tube, different types of badges measuring different gases. We have mini volume filter samplers as well. The advantage of these are that they don't necessarily require any sort of power or electricity. So these can often be used in areas that are more rural, that don't necessarily have access to electricity. The one shortcoming that we have when doing this is the fact that we don't get that high resolution differentiation that we need when doing exposure studies, because we're interested in what activities relate to the exposure that we're seeing, right? And what those exposure measurement durations are, right? So yes, they do provide us values for where we do not have anything, but if we have to do it at a higher resolution, it can also be very time consuming to use this method of approach method. Yeah. I now want to go into a little bit more on the developing technologies. I think most people within the air quality space have endlessly talked about low-cost sensors within the last couple of years and the development and use of these, especially within Africa as well. Right. So for PM specifically, as I mentioned before, the low-cost sensors are mostly based off of optical particle counters or nephelometers, which are light scattering. Right. So these are the two main approaches or sensors used within the low-cost instrument space. And how these usually work, it's a miniaturized version of a reference type instrument. Right? So we have a little pump that draws air through the sensor detects, and through a electronic board, we get a value that is then, or input that is then output as a measurement value for us. The thing with these sensors, they're all based on different algorithms. These different algorithms depend on the manufacturer that actually installs that specific sensor within their instrument. Okay, so these are usually provided as black boxes mostly, so we don't really know what's going on within the internal structure and calculation of those sensors. So when using these low-cost sensors, we need to take that into consideration as well. So the positive thing about using low-cost sensors, specifically for PM, we have the ability then to augment our networks, right? So we can cover a larger area at a lower cost, right? So this is not just for ambient monitoring, but it can be for indoor or personal monitoring as well. And we still get a real-time or continuous output or data value from these, which is, in my opinion, more useful than having filter-based samples that are integrated over time. Okay, so if you consider that, we have a lot of possibility to use low-cost sensors, specifically in the African context, regardless of whether you're doing environmental-based studies, whether you're doing health-based studies, whether you're a citizen scientist that's just interested in the basic technologies. There is a lot of potential use for these. However, we need to understand that these instruments are very, very sensitive to seasonal changes and temperatures. The longevity of these sensors are always in question, right? We do see that these sensors have a larger unit-to-unit variability, so inter-unit variability, and they do drift over time. So even though it's a low-cost sensor, it's also not just a plug and play. We have to take into consideration that, yes, they are lower cost compared to reference grade instruments, but they still have the same type of assumption and limitation associated to them with them if you think about the data itself. We'll talk a little bit about the comparison, how to do that a little bit later, but I just wanted to highlight those aspects for you. And if we move to the gas-based sensors for low-cost sensors, just as a reminder, mostly electrochemical, metal oxide, or NDIR based. These sensors usually drift when it comes to temperatures, so they are highly impacted by the temperature and humidity, and they can sometimes be cross-sensitive with other pollutants. So if you have a very complex or matrix of pollutants in your environment, especially with, for instance, in peri-urban or urban environments where you have industrial, residential, traffic, etc., all of those pollutants coming together, these sensors can be very cross-sensitive to the different pollutants in the environment. As I mentioned, temperature, relative humidity, key factors in any of the measurements that we do, as all of the technologies are impacted by it. And so it's going to impact how the sensor actually reads and interprets the data. And a lot of the time, temperature and humidity is included in the algorithms that are in the black box, to say. So it bases your concentration that you see on the input it receives and corrected for by different environmental conditions such as temperature and relative humidity. Right? So usually in the optical PM sensors, we have a positive bias. So when we have higher relative humidities, we usually see the hygroscopic growth of particles, which is related to the particle physics and chemistry, right? So we see that positive bias. With electrochemical gas sensors, we usually have drift with temperature. So as temperatures increase or decrease, we have an additional drift in the output we get from that. And considering that all of these sensors need a higher calibration frequency to them, it is important to consider where you deploy these instruments, as the calibration that we get from a single microenvironment might not be transferable to other microenvironments. So when we sample in an indoor environment, but we use an ambient environment correction, that brings in bias into your data, for instance. Yeah, so those are some of the other things that we need to consider when using these instrumentation. So my personal rule of thumb is that if you do use, whether it's reference grade instruments or low-cost sensor instruments, if you do any type of environmental monitoring, include meteorological data, whether that's a larger meteorological station or whether that is just simple temperature or relative humidity measurements within the microenvironment that you're working with. That is very, very important. And it's going to tell you more about your data. It's going to help you to interpret your data a lot better and find correlations that you might not have thought about. Okay. So when it comes to quality assurance and quality control, we need to think about not just when we work with data, right? We have to think about the whole sampling process, right? So how does quality assurance and quality control look like before deployment, within the field, during the actual operations? So when we're doing the active sampling, how does that quality assurance and quality control look like when it comes to the calibration or maintenance checks of our instruments? And then also having a documented metadata traceability, that if you are in your data analysis process, you can refer to and make sure that you have a very, very, very clear metadata sheet that helps you to interpret what you see in your data as well. I think most people tend to not put emphasis on the metadata. They have some sort of traceability, but it's not usually not detailed enough after the fact when you have to go look back at those things. So here, I think the key thing is that we not just think about the post-campaign aspect of quality control and quality assurance. In each step of your method, there should be some sort of quality control and quality assurance aspect to it. And then I think one of the other things that I just want to mention as well is that even though we usually have specification sheets with instruments, most of the newer low-cost sensors, initially when they came out, they didn't all have specification sheets. So they should just say, this is the sensor, this is what it measures, but there's no additional real information as you would receive with a reference grade instrument. This has slightly changed over time. So we do have those improved specifications with the newer instruments coming out. It's important to keep track of those as well when in your metadata, along with the actual just general workflow of your study as well. So when it comes to calibrations, here I'm talking in general calibrations, not just reference to low-cost sensors, but in general, when it comes to calibration of instruments, there's mainly two approaches that we take. We either have single instrument calibration or network calibration. So for single instrument calibration, we usually have one reference station. We have one or two or three low-cost sensors with that. We co-locate, we get a correction, and we adjust the measurement values according to that correction. For a network approach, that is slightly different. This is usually where you have a single calibration, single reference station, or two or three reference stations within your network, and you then have a sensor network which consists of maybe 100 or 200 or 300 different other sensors, and you then transfer those corrections that you get from the anchor reference stations to all the instruments within that network. Right. So this is where we usually talk about transfer models, and that usually gives us a map or gridded output when it comes to our data and corrections. Another important factor that I just want to mention is that we do not only just consider field calibrations. Field calibrations are sometimes the easiest point of view, and I think for me the most important, because we know that instruments differ within different microenvironments. We actually want to do the calibration in the type of environment that we're sampling in. So then we know that the correctional calibration that we apply is suitable to that specific microenvironment. It is an example of this that I can use is, for instance, if you're sampling in an indoor coal burning environment, but you're applying an ambient biomass burning correction factor to your coal burning environment, you might in turn either overcorrect your data or undercorrect your data when you apply the different microenvironments calibration factor to it. So just take that into consideration as well. And then we also have laboratory-based calibration, where we can have a more controlled setting for doing calibrations. This is usually where we would, over a range of temperatures, relative humidity, concentration conditions, we would then calibrate at different points. This is more to test the actual instrument than it is necessarily calibrating for a specific microenvironment. This is just an example of how metrology is incorporated in air quality monitoring. As we know, temperature, relative humidity, pressure, those are very important in how our instruments perform. These images are actually met stations that were placed throughout the Comrades Marathon in 2024, 2025, where exposure was measured for athletes along the route of the Comrades. So if we don't have those met variables, we have a gap in actually interpreting the aerobiology parameters that go with that, so the pollen parameters, as well as the PM that was measured at those sites, right? So we will have a concentration, but we'll have no additional information about where did that actually come from? Did it come from a specific wind direction? What was the temperature and relative humidity exposure like? Because temperature and relative humidity also affects epidemiology studies, right? So these are two very specific variables that I think is extremely important to include in all studies. Then I just want to highlight the three main environments that we actually do air pollution monitoring in. We know the ambient environment, the indoor environment, and then the personal. But these environments are not all separated from each other, right? So yes, I'm in the indoor environment, but my personal exposure is maybe limited to where I'm sitting at my desk now, not necessarily what's going on in the other corner of my office. Yeah. So we need to think about what are we actually trying to measure, in what environment are we actually trying to characterize when it comes to air pollution, right? So for the ambient environment, we usually have fixed sites, which are outdoors. These can be either short-term or long-term sites, depending on the study or the aim of your study specifically. And these are usually very sparsely located spatially, right? So they are normally, if it's long-term regulatory sites, they would be in industrial areas, maybe residential areas, high traffic areas, maybe places like harbors. But they are not necessarily located in areas that actually have high ambient pollution. Right? Within the indoor environment, these we usually consider to be places like residential homes, specific, if you're looking at a specific exposure area in the home, for instance, a kitchen. We can look at school classrooms, for instance, as an indoor environment, or even our vehicles that we travel in. Right? For personal, this is usually at that specific moment, where am I, what am I breathing in, and how long am I exposed to that specific concentration. The personal exposure in itself, I think, is the more important one when it comes to exposure assessment of specific population groups. And however, the personal exposure can be sometimes a little bit invasive because people actually have to wear monitors. They have to wear it for an extended period of time. You have to engage with people a lot. Where with ambient and indoor, you can have a sensor in the environment and have it run for a period of time, which is a little bit less invasive, especially if you're thinking about sampling in communities, right? So in residential communities, for instance, that plays a huge factor. Yeah, this is just a few pictures to kind of show you some of the ambient-based air quality monitoring deployments that we've had. In the top picture, we have the center, we have the TIOMs. We also have, let me just get my pointer out, sorry about that. So here you can see that we have a TIOM, which is a beta gauge. You can see that this is the heated inlet that I spoke about. And this pipe goes out to the ambient environment where it actually has an inlet on it, this outside inlet. And it's sampled through, there is a part of the tape that you can see. To the left of that, we have a GRIM, which is actually a nephelometer-based instrument. We also have an ethylometer, which is a black carbon-based instrument. It also has a tape inside, and it converts the attenuation or absorption to a concentration value. Here we have a Picaro instrument. This instrument samples a few of the more volatile organic compounds and species that we don't necessarily include as part of our regulatory monitoring. We also have, for instance, the gases that we actually use to calibrate. Here is a different station. You can also see gas analyzers, also a Picaro, and here you can see an open example of what that beta attenuation looks like with the tapes as well. To the center here, we have also a beta attenuation instrument, but this is a mobile version that can be deployed across a higher spatial region. So they're a little bit more compact compared to the AQMS versions of it, but is also primarily used for ambient or outdoor sampling. We do sometimes convert these to be able to run off solar, depending on our situation with electricity and monitoring space that we're specifically in for that. Then for household air pollution monitoring, this is where we have to consider the combination of both the indoor, ambient, and personal altogether. Right. So this is typically where we look at things like have studies that focus, for instance, on using improved cookstoves as an intervention to reduce emissions within a residential community. In order for us to actually determine that, we have to have an understanding of what the ambient environment is like in the community. We have to understand what the indoor environment is like in that community, not just within a single household, but across a few different households within the study. And we also need to understand what the personal exposure looks like. So how much time people actually spend within the different environments to assess that whether there was an increase or decrease in actual exposure to that person by the amount of time they spend within a specific environment. Yeah. So this is also an example just of an improved cook stove study that we did within one of our communities here in South Africa, and our students who were involved in that and engaging with the community on that as well. Then on the personal exposure side, this is where we then have the direct estimation of what the person is exposed to that you are targeting within your study. These are usually done through wearables, and typically you have to GPS track people in this situation to actually know how much time they spend within the specific microenvironments that you're interested in. A less invasive version of that is to have participants actually keep a written log of the amount of time they spend in the different environments. But I find that this is less accurate, and sometimes participants can forget to enter specified times in areas, right? So if you are able to, the better approach would be to include a GPS tracker in that type of setting. You also have an example of a few different types of monitors that we use in both the personal and indoor environment. So here we have a dust track monitor, which has the ability to size differentiate between PM1, 2.5, 4, and 10, as well as total. And this is usually used for the indoor environment as a stationary monitor. And they are typically quite reliable because they are light scattering. They do tend to overestimate a little bit. So even in this situation, with a higher cost instrument for the indoor environment, you will still have to do a gravimetric calibration with a filter-based method to make sure that you're applying the correct correction to this instrument. In turn, this instrument, if it's calibrated correctly, can potentially be used as a smaller co-location reference equivalent for low-cost sensors. So if this one was calibrated against a gravimetric reference, you could potentially use that as an indicator within the field for deviations for other low-cost sensors. To the right of that, you have an example of just a normal pump and a filter-based sampling. So that is the gravimetric sampling happening here. So this filter is then compared to these measurements to get a correction for the instrument. Okay. This is an example of the actual exposed versus non-exposed filters within this indoor environment. And here to the right on the sampling table, we actually did a intercomparison between 3 different versions of indoor and personal monitors, which included the dust track, both the old and the new version, as well as a side pack as well, to see how those instruments intercompare with one another as well. So these are some of the aspects that can be looked at when you consider personal monitoring. Some of the negative aspects about personal monitoring, as I mentioned, it's participant compliance, right? So, and the burden towards the participants. And I think that is very applicable to epidemiology study or exposure studies. If you have a health focus to your work, is that I think you have to be able to select the correct participants from the start, right? So we have had previously that we've monitored a participant for a few days, and after that they decide, no, they're not interested in this. It's too much of a hassle for them to actually carry these instrumentations. So that is something that you have to consider when considering these personal exposure type of measurement campaigns. Another thing is more recently, these devices have been improved a little bit when it comes to like the weight of the instrument, how much noise it actually emits, depending on whether it's a pump-based or filter-based, whether it's a passive. So there are options in that. So depending on your specific target audience, I think those you'll need to research a little bit more on your own. But there are options within that as well. Okay. Then I just want to highlight a few other monitoring expeditions that I think a lot of the time gets left behind. Even though we focus a lot on what the exposure of people are, in order to understand that, we need to understand what the exposure in the environment is like, or the emissions in the environment is like. This is just a comparison. For instance, to the left, we have what we call stack sampling, which is more for industrial purposes or industry purposes, where we actually measure the emissions that come from an industrial stack. And to the right, we applied that same concept to doing emissions measurements on a chimney within a low-income residential community. So to better understand the emissions actually coming from the fuel source they use within that specific household and with the type of stove, so the ignition process, etc., we applied an industrial-based methodology. We minimized it slightly, and we applied that to a residential environment. Another one is, for instance, road dust monitoring, which in more rural environments where you have more unpaved areas in residential communities, this would be one of the sources that highly impact exposure within the community. And this is an example of where we have traffic counters. So it also counts how many vehicles actually move across that space. Within these, we have 3 to 4 different dust track monitors. So those blue monitors that I showed earlier, those are within these environmental boxes. And we sample that, as well as you can see here at the back, there is a met station as well. So incorporated the metrology, so we can see at this ground level, specifically the level where we're measuring the PM, what was the wind direction, wind speed, temperature like for that specific sampling height. Yeah. So this is an example of a road dust monitoring that was done in one of our communities. And then this is also another example of more of an environmental emission, which is biomass burning. So our felt fires, especially within our biomass burning period, August, September, October, as well as December in the Kruger National Park, we were interested to see actually what the composition was like for those pre-burn emissions. So for this, we have an ES642, which measures PM. And in this case, we were interested in the PM 2.5 fraction of it. We also have a wind speed, wind direction, and temperature sensor mounted on the vehicle. The vehicle was located downwind of where the actual burning was taking place, so we could measure what were the emissions from those. And along with that, we did actually in-plume measurements, where we had a gravimetric filter-based method that we used, where we sampled during specific phases of the biomass burning process, during the ignition, active, and smoldering phase, as these usually have different chemical signatures associated with them. So this is just another way in which we have combined both gravimetric measurements with continuous measurements to actually answer questions that we had regarding biomass burning in this specific environment. So recently we have had a growth in, I think, African-based published, peer-reviewed published work, specifically when it comes to air quality measurements, both ambient, indoor, personal, epidemiology-based studies. So I think there's truly a growth in that, and I think that's because of the availability of these types of measurement technologies within Africa itself, which I think provides a good picture of what the future would look like for these type of measurement campaigns across Africa. Even though there's been an increase, we still have a large data gap in Africa and across Africa when it comes to actual air quality data, right? And due to this gap, it means that geographically we are underrepresented in the global context when it comes to all types of air quality studies, not just in epidemiology, but in general air quality studies as a whole, right? So what this means for us is that we have a few difficulties because of this data or the lack of data that we have. And some of these difficulties arise from we aren't able to then generalize over large areas because our networks are set up in such a way that there's a large gap between some of the geographic regions. So we can't really interpolate what happens in those unmonitored areas. We also need to understand that not everybody applies the same level of monitoring when it comes to their different research projects. So even using data from other sources, secondary data that you yourself were not responsible for, it is sometimes difficult to actually use that data properly because it's not recorded properly. So the metadata, the specific project descriptions, all of that, there's not a standardized method of that across Africa, which makes it very difficult to compare data across different regions in Africa as well. I've more recently seen a lot of studies that start to integrate satellite data a lot more as a supplement to ground-based measurements, which I think is helpful. But we should just remember that satellite measurements cannot replace ground-based truth measurements, right? So we just need to keep that in consideration. So in my concluding slide, this kind of, I try to summarize a little bit about what I think is important for when trying to go about selecting the correct monitoring method or approach for your study. And I think the important thing here to highlight is that choosing the right method is not, it's not a recipe, right? You have to, in the context of what you're trying to do, think about the logic behind it and will it actually be applicable to me? Even though somebody else did it in this way, will it actually work for what I'm trying to do in the environment that I'm trying to do it in? And a lot of the time we find that some of the methodologies used for non-African countries don't really translate to what we're trying to do just because of the different types of limitations that we sit with in the African context. So I think that's something that really needs to be in the back of your mind when thinking about these monitoring aspects for your study, right? So I just want to highlight, so I think for regulatory compliance or trend analysis, it's usually just for a few very specific sites. And you usually have reference-based methods for this. They're usually linked to very set standards of maintenance. They go through audit processes, traceability, etc. Right? If we think about epidemiology, we usually think about this in context of either a town or a city or a region. These can have a combination of reference instruments, low-cost sensors, as well as passive samplers. And needs to incorporate some sort of co-location and metrology as well. For source and portion-based studies, where we want to see what the chemical compounds are associated with the particulate and gases that we actually measure. In this, we need to consider filter. We definitely need to consider filter-based sampling for the chemistry, but we also have more recently have the development of continuous measurements that can actually break down these chemical components as well. So have a combination of that. There has to be a well-documented process of the gravimetric lab-based activities there and well-documented protocols as well. For household and personal exposure, this is more on a microenvironment level or participant level in itself. You have to consider gravimetric, other variables such as your carbon monoxide, your black carbon, which is more through absorption measurements. You have to think about time in space, right? So how much time do people spend in specific areas of the house, as well as non-negotiables in this is actually being able to trace the time of people, as well as, again, well-documented notes and metadata in that. And then what I already mentioned, the spatial gap filling, where we include satellites along with reference and low-cost sensors through ground truth validation. So these can help us on a regional or country scale or even a subcontinent scale if we need. And I think that's it from my side. I hope I covered everything, and I am open to questions.
Thank you so much, Brigitte. I think that was a quick run through monitoring. You covered all the bases as was the intention of this session. And I think the last slide actually summarizes it in a very good way. In a sense, fitness for purpose. What do you actually want to do? What is your objective? And what kind of monitoring is available for that? And I like something that you put in there, which is a non-negotiable quality assurance. There are some things that you actually are a bare minimum, depending on if it's a regulatory or exploratory studies. And I think just appreciating that we have a broad in terms of expertise and areas of organizations, a broad spectrum in terms of the participants that we have on the call, from policymakers to I've seen PhD students, researchers, experienced researchers. So I think it's very pertinent, that last slide, to what everyone on the call does on a day-to-day. So it's time for discussion and or Q&A rather, but I think we'll make it more of a discussion. So I think my role here is just to summarize a few of the questions, and I'm starting to look at the first few. So I'll bundle the first set of questions from Noor and Rose. So Noor is asking Brigitte, can you compare measurements from optical counters, essentially the local sensors for PM, with BAMs and TIOMs? And Rose is also asking if you can explain how to carry out the calibration of the local sensor during collocation with the reference monitor. So maybe we can start with that as I think through the next set of questions. Yeah.
Okay. So the first question is on how to actually do the collocation with TIOMs or BAMs, right? So
yes.
I think it depends on where you want to do the comparison, whether it's in a laboratory or a field environment. I will speak mostly on the field calibration, as I think that is one of the important parts of this. Within the field, it is for the setup of the co-location, it's important that your instrument sampling heights are at the same level, right? So if your reference instrument sampling height is at 3 meters in the ambient environment, you need to put your instrument your instruments in at that same height, so you're sure you're sampling the same air mass. Yeah, so that's one of the important things. For the duration of the co-location, that is going to be dependent on what you're going to use the calibration for, right? So, but ideally, I would say nothing less than like 7 days, because then you kind of get an idea of the temporal variability as well, and your variability with the change in environmental conditions. So as your environmental conditions change and the concentration level changes in the environment, your calibration changes, right? So I think it's important to get that diurnal variability and also your concentration variability in that specific environment that you're looking at, because it doesn't help you put a sensor in an environment that is very low in concentration, and at lower concentrations that sensor is not picking up the trend. As for the actual correction, that is dependent on the reference information you have available, as well as what your instrument itself is measuring, right? So if your instrument is only measuring PM, you do get instruments that only measure PM. They have no temperature, no relative humidity. They just measure the PM. And then you get instruments that have a combination of the sensor with met variables, and those are within their context, right? So if you don't have temperature and relative humidity measurements available in the field, then that's going to change how you're going to approach the calibration, right? So your method of calibration, there are a lot of different ones. So you get your physics corrections, right? So based on hygroscopy, based on the physical properties or change of properties of particles based on environmental conditions, things like your dew point changes, etc. Then you get your simpler linear regression corrections, right? So ordinary release square, so where you compare it to a reference, get a correction, apply that correction to your data set. Then you get more multilinear type of approaches where you have your different covariates that come into play. So your temperature, relative humidity, you can even bring in pressure, you can bring in solar radiation, all the different types of variables that you measure. You can bring in that as covariates in your correction as well. But the correction that you need is going to be dependent on your environment, right? So if you have a very complex environment that you're monitoring in, for instance, where we sample in the Vaal region, where we have a complex mixture of air pollutants with extreme deviation in or ranges in concentration, as well as temperature, as well as relative humidity, wind speeds, those aspects, they all come into play. And then we also have machine learning approaches as well. So this is where you can have your local sensor, and based on a calibration test run, you build an algorithm, and that algorithm is applied through machine learning and improved through machine learning. The difficulty is there that you can't always explain what the model is doing in detail, right? So that is where it's more of a statistical based, also kind of black box. So if you're not very versed in the modeling approaches and machine learning itself, it can be very complicated. But then you also get approaches where you combine those. So where you can combine a physical correction with a linear regression and apply a machine learning correction as well. So you build a model based on different parts of that fit your methodology or approach, right? So what you're trying to do. So it just depends on, ask yourself the question, am I getting a good enough correction using physical corrections or OLS or ML, multiple linear regression? Is it necessary to go into that depth of doing a machine learning approach, right? So it's just going to be dependent on what you're trying to do, but there are a lot of different corrections that can be applied.
Thank you for that. And just to add on that, also based on something you said, that the literature on monitoring is actually now a lot on the continent. There is
it's on the increase, definitely.
Exactly. So there are papers that you can look at that have done all sorts of things, including machine learning and all these things for their correction. So you can also look at that literature in terms of determining what works for you.
Yes. So the one thing that I've noticed about all of the LCS papers in general is there's not really a consensus on what metrics they're using to test, right? So you have your obvious ones, right? So your mean bias error, your root mean square error, those ones, but most of the papers don't report it in the same way, and it makes it difficult to cross-compare studies with one another. The other thing is that the approaches in the correction, so the model corrections, is also very different in those papers, and not all of the papers actually define exactly their setup for the model, which also makes it difficult to. So if I want to rerun somebody else's approach, it becomes complicated, right? So I think And there are so many different types of models and approaches that mostly papers focus only on the common ones, right? So it's getting there, but there's a lot of variability in how it's addressed.
Yeah, thank you. So the questions are coming in thick and fast, so I would like to keep it for now. I'll come back to Sam's question, which is very specific to Namibia. I'll just like to keep it on the reference monitors for particulate. So Caroline is asking if you've experienced any issues with bumps or TIOMs because of dust, wildfires, dust storms, and what would you recommend for as a way of proactively preventing these types of issues with such
Mm.
equipment.
Is that specifically for Namibia?
No, this is
Or
generally for,
is it a general? Okay.
yeah,
So
generally, yeah.
so generally speaking, I myself have not really experienced any issues with regards to the beta attenuation TIOM or GRIM, right? So these are the ones that we typically interact with the most. Mostly the BAMs, so the beta attenuation and the GRIMs, and occasionally the TIOMs. So me working with them, no, not really. I haven't really experienced those issues, but in Namibia, we have experienced dust storms before while doing monitoring. And the key thing there is that if you do get a dust storm, the thing that you're going to have to do is you're going to have to clear out your inlet. So that's the key thing. So I don't think there's another way of addressing that specific issue. If you're in a high dust environment, your maintenance is going to increase, right? So the time between you actually doing those maintenance activities. So for instance, in an environment that in a rural environment where I don't get a lot of dust storms, there's dust, right? There's road dust, there's all those things, but it's not a high quantity of dust being resuspended for an extended period of time. I think we usually do about every 3 to 6 months, we do a proper deep clean, so deconstructing the whole inlet. But I think in a high dust environment, you're probably going to do that on maybe every 2 to 4 weeks to help out with that.
Thanks. So Sam is from Namibia. He's appreciative of the presentation, but he's wondering whether, based on what you've projected for Namibia, whether that data is available or accessible. And he's also interested in wearables, if you can say a bit about wearables and the role they play in the
Um,
monitoring space.
yeah. So for Namibia, we've been mostly been active in the Henties Bay region, Walvis Bay region, and then into Gobabib, which is the Namib Desert Research. I think if Sam's from Namibia, he'll know. So at Gobabib, they have a wide range of instrumentation that is sampling, and you can get access to that data. I think you can just go to the website and ask. They do have also international partners that have instruments set up there, right? So you might have to go through them to get to the international partners, but that's one way of doing it. There's also national databases like the FOG network is there. You do have some monitoring stations. You do have a lot of met stations in Namibia. So there's national networks there, and you can request the data for that as well. And they have the typical variables, temperature, the relative humidity, etc. Gobabib itself is a nice research space. It's a regional background site, and it's used for satellite validation. It's used for studying your transboundary pollution and the movement of pollution. So we actively have instruments there as well. And we actively work with international partners there as well. So a lot of people from France, Germany, those type of countries. And yeah, so and that varies from PM to gases to volatile organic compounds. It covers the whole range. There's sun photometers. There's now I can't think of the name. I'll probably remember later. But there's a lot of different research focuses in Gobabib itself. It's not just air pollution based, but generally in environmental sciences.
Thanks. So the next sort of questions, I'll bundle them together. Janine and Eyali are essentially asking how we can use this data for health studies. And there is a reference to, do we need to go beyond mass and try to look at the chemical composition of what we are measuring.
Yeah, so we can't do health-based studies if we don't have the supporting data. Okay. So in order for you to determine what the actual health impact potentially could be, you need to have an understanding, and that's where that where the first diagram in my presentation, we'll share the slides afterwards, but that first kind of flow diagram that shows from emission to exposure impact, that's kind of the process. So if you don't know what your sources are, what the chemical and physical properties are of the pollutants that come from that sources, how long you're exposed to, what the concentrations are, how long you're exposed to that concentration, the dose, you can't really determine what your exposure is, your personal exposure is. And then based on the chemistry of that, that is where your health impacts come in. Right? So the impacts it could potentially have on health. Right? So without the baseline measurements, you can't really do anything. The important thing there is that depending on what health aspect you're investigating, you need to make sure that you're going to be interested in a very specific either PM, right? But PM is broken down into different chemistry, which is where we talk about source apportionment, right? So my PM2 consists of so much silicon, so much volatile organic compounds, so much black carbon, so much of this, so much of this. So that builds up a profile of the PM that people are exposed to. And that helps to determine the base health impacts that it could potentially have. Yeah, so that things like your heavy metals are important there. But depending on what you're studying in the health environment is going to depend what you're interested in exploring further when it comes to breaking down the sources of the PM and gases.
Exactly. Thank you for that. So Aisha is asking about data reliability. What advice would you have for young researchers interested in air quality research? There is issues to do with calibration and validation of low-cost air pollution sensors prior to field deployment, and resources are limited. Lacking actually. So, what advice would you have? Yeah.
So I think it's definitely true. That is, it's not everybody has the availability to the same resources, which is a very, very true constraining factor in our research that we do. We are fortunate enough to have our own reference stations and collaborations with the government that we have reference stations available where we can do research, right? So that helps. But I think if one of the ways in which, say, you don't have a reference station available, right? I would at least try, if you have a contact that potentially has more resources than you, if they'd be willing to at least co-locate like a medium to higher grade instrument, not necessarily reference grade. So that is, for instance, like the dust track that I spoke about earlier, where you can co-locate that with your reference and get a correction of that and use that as a transfer reference monitor, if that makes sense, right? So that's one approach that can be taken. But I think it does limit you, right? So it's a difficult problem to solve if you don't have access to the reference stations or reference instrumentation at least. But that's one approach. And I think that's one that can be feasible for more people, because I think there are, most people do have those moderate to higher cost, at least one or two instruments like that around or access to, which could potentially be used. So if we tend to understand the moderate to high cost instrument assumption and limitations a little bit better than we do the low cost sensors. There's still assumption and limitations, but they've been used for a longer period of time. We've worked with them, they've been published. There's a lot of different correction factors for a lot of different environments for those types of instruments. So that is also a helpful approach to be able to take on that. Was there a second part to that question? Sorry, Victor.
No, I think you've covered it.
So some advice on data reliability. Okay.
Oh yeah.
So I think that's a very important part. My key thing there is keep track of your metadata. I think a lot of people don't place enough emphasis on this, and then post analysis they come in and they say, okay, well, I can't remember what happened on day 14 of this campaign. There was something, but I didn't write it down. So keeping track of your metadata, that's with instrument models, instrument serial numbers, date of deployment, time of deployment, when did the power go off, when did I do a inlet clean, all of those things are considered metadata and are extremely important. The other thing that I think is not leaving your instruments for extended periods of time before looking at the data, right? So sample for a day or two, do a few hours, download the data, or whether you check it online or whatever your setup is, get access to your data, plot your data, check your data to see if it's actually giving you something that makes logical sense, right? Is it just noise, or is it showing a pattern, a diurnal pattern, kick up some dust near the inlet and see if it makes a spike, right? Those type of things, right? So test to see if your instrument is responding correctly to the actual measurement process. Also, then weekly checks, right? I wouldn't go more than a week without checking your data or checking your instrument, even if it's remotely, right? So just check in on your instrument. And then just keep with normal statistical practices when it comes to data analysis, right? So don't overcomplicate it too much unless you're exploring a very specific thing, like looking at different calibration models and things like that. That is where you're going to statistically explore and build your own stuff and try and figure out what works best. But otherwise, just keep to the basics. The basics are often the best to use in any case.
Yeah, thanks. And I think you've already answered the questions we have from David as well, on how to sort of make sure you're getting QA/QC procedures and reliable data from some of the work he's doing. So next one, I think a very interesting question from Arthur here. So there's common mistakes that we make on the continent in terms of monitoring low cost versus reference grade. Are there any approaches you think that countries in our settings can use? Any recommended calibration, validation, and data quality assurance in sort of humid, dusty, power is not stable sort of conditions?
Yeah, so I think the US EPA's document on kind of just the general setup of how to do a co-location study I think is a good baseline to use. So it gives a good standardized baseline of, include three low cost sensors, because you have to check accuracy and precision, right? So inter-unit precision is a very important thing when it comes to low cost sensors, right? So there is inter-unit variability. You might find that two of your sensors are very precise to one another, but when you compare it to the third, then all of a sudden your third instrument is way out, right? Or 10 micrograms per cubic meter higher than the other two, right? So that in a network can become complicated, right? So you might have 3 or 4 or 5 sensors in a 20 sensor network that are reading above the average of the network, right? And that can skew your data a lot. So don't just check reference to low cost sensor, check low cost sensor to low cost sensor as well. Okay, so that's one of the key things that I think sometimes is missed in the low cost sensor comparison study. So they talk about the reference to LCS, but they don't talk about the inter-unit variability. And then, so I think standardization. So I think it's a difficult question to answer if you think about things like power instability and things like that, right? So ideally, you would want a reference site that has the capability of having at least like a backup source of power, especially if it's a long-term study, right? I mean, for instance, we struggle with electricity a lot. As you know, in South Africa, we have a lot of load shedding and so forth. And that was definitely would have been a problem for our low cost intercomparison study if we did not have our reference site at a site that has backup generators, right, for instance. So things like that do make a difference. There's not really a proper solution for that other than if your low cost sensors are running on solar, that's fine. But then again, you have to think about if it's not on solar, what type of battery backup does it use, etc. Right? So those are reference stations are a little bit more difficult. If you don't have like a generator or a solar solution for it, you're going to lose data for that period of time, right? Because it has a higher energy requirement than low cost sensors.
Yeah, thanks. So I'm not seeing a lot of questions on the gaseous pollutants. So I will summarize a set of
Mm.
questions on use of satellite data. Essentially, for national or regional level, what do you think about the use of satellite data alone, especially where ground monitoring is
Mm.
scarce? And how does that provide a homogeneous, synoptic, and continuous view of the entire sort of territory?
So I do think satellite observation has its place, right? Because if you're looking at satellite observations, you are generally looking at a larger area, right? So either sub-regional, regional, or um, continental scale, right? So I think in that instance, if you can set up your domain to at least have one background reference. Right? So for instance, if you're looking, I'm using Southern African as an example because I'm more familiar with the Southern African context. But if you look at using satellite observations in Southern Africa, you would ideally want your domain to include a place like Gobabib, which does have the measurements, long-term measurements, and it has most of the variables that you were looking at to be validated, and it is a regional background site, which means that it is not directly impacted by specific sources other than resuspended dust from the immediate environment. But it's not impacted by biomass burning. It's not impacted by residential emissions, etc. Right? And then we would typically try and incorporate something like the Cape Point site or more in central Gauteng, for instance. Right? So that is typically you would try and set up your domain in such a way that you at least have one background site for ground truthing. Um, but I think satellite data can provide very, very good information on the general state of things across the region. I think you're on mute, Victor.
Yeah, I was just trying to find the unmute button
Okay.
there. Sorry.
That's fine.
So thank you. I think we are almost at time and we have a
Mm.
lot of questions. So what we'll try to do is take them off the chat and answer them and put them in a document. I think we've covered most of them actually, but if we see any that are interesting, I think we'll summarize them and have them accessible to the website. So as we close, thank you, Brigitte, for your time and sharing your knowledge with us. We really appreciate. Um, for the participants, we do have a link to a survey where you can sort of um, tell us how you found this session. There is 3 more to come again in the next couple of weeks. I think we've covered the bases in terms of the monitoring landscape. We have representation from more than 20 countries on the call, all the way from Mozambique, Namibia, South Africa, Kenya, Uganda, Rwanda, up west, Nigeria, Ghana, Cote d'Ivoire, Senegal, even the US, Thailand, and India. So thank you all for finding the time to be with us. My colleague Pallavi is in the background. I forgot to mention her. Sorry, Pallavi. She's been doing most of the in the back sort of firefighting. Thank you for your time, Pallavi. And as she posts the link to the um, short survey, I would like to say because I believe there's a lot of students also who are here. We have just recently launched a fellowship program, Future Leaders Fellowship Program in collaboration with the Africa Clean Air Network, which is an exciting one for us as HEI. So it's open to masters and PhD students across the continent. And it's a 6-month fellowship. A lot of the details are available on the website. We will share the link as well for that. So we welcome you to apply, and I look forward to reviewing and receiving your applications. So once again, as we finalize, I'll just give it a few minutes for anyone who wants to access we'll leave this open for a few minutes for anyone who wants to access the SurveyMonkey link, fill that up. And we look forward to seeing you at the next session, where we will look at approaches for exposure assessment. Today, we have looked extensively at monitoring, what technologies are available. We'll now start going specifically into the techniques that we apply for health studies going forward. So we look forward to seeing you in that one. And from me, enjoy your morning, evening, afternoon. All the best, and hope to see you soon. Thank you.